Okay, so obviously we did our lab on position versus time graphs yesterday. Okay, it's pretty straightforward. Once you've got the graph built, the analysis is not going to take you very long. Okay, remember to put in your conclusion where you copy and paste your hypothesis, and then you give me an explanation as to why it can be accepted or rejected that uses the data you have, like the shape of the graph, etc. Okay. For your sources of error, just a reminder, I was marking a Science 10 lab this morning, and it's probably important to mention this for you guys as well. Sources of error have to be sources of error that are inherent to the procedure that you could do nothing about. You followed the procedure, and this could still be a source of error. It cannot be human error. Okay? So if you have a procedure and you don't follow it, and you make a mistake, and then at the end you go, sources of error. Well, I didn't do this. Okay? That's like the worst thing you can end off a report with. Okay? It basically screams to me, hey Coder, I know I didn't do this right, but I was too lazy to go back and fix it. So my whole lab is invalid. Okay, like you just don't want to say that. Now, something that's inherent to the procedure or the environment that you couldn't change and just had to deal with, that can be a source of error, like the nature of the floor. Okay, you didn't really have any choice. I told you to do the experiment on the floor, and you did. Okay, were there sources of error there? Certainly. How could we correct it? Well, there's probably ways to fix that in the future, but you couldn't do it on the day of the experiment. Okay, does the difference make sense? Okay.
Would the delay for the app, would that?
It's not going to be no, because it didn't interfere with you getting valid data, right? Everybody was still able to get a good line. And I told you, there's a delay, here's how to fix it. Right? Here's how to account for it. So it didn't interfere with us. It was inconvenient, certainly, but it didn't interfere with the collection of good data. Yeah. Okay, so today we're going to look at velocity versus time graphs. Okay, velocity versus time graphs can show us the same trick or same set of data from an experiment, but from a different point of view. Okay, so case in point, the two graphs that I have on the screen right now. This one is a position versus time graph. What is it showing? What kind? Positive and consistent or constant, right? This is something traveling at a constant, positively directed velocity because its position is changing by the same amount every time interval. Agreed? Okay. That velocity versus time graph over there on the right, is it also showing an object traveling at a constant velocity? It is. Okay? But lots of times we look at that and we go, oh, the line's horizontal, so nothing's happening. If I have a horizontal line on a position time graph, nothing's happening. The position isn't changing, the object's not moving. All that's happening is time is passing. Okay? But on a velocity versus time graph, something is happening. Okay? This object is traveling in a positive direction at a constant velocity. The velocity is constant, and so it's not changing, and that's what the graph is showing. Right? Does everyone kind of follow the difference? This is something I can get people on a multiple choice question on the unit exam. Okay? This is why it's so important to look closely at a graph to see what kind of graph it is. If I put that picture on the right on a test and say, what's happening in this graph, A, B, C, or D, and one of those options is nothing, you'd be surprised how many people will pick it. Okay? Because their gut reaction is, it's a horizontal line. Nothing's changing. That's true. Nothing's happening isn't necessarily true. Okay? Everyone follow the difference there? Okay, so it's just one of those things, you know, I get it. It's on a test, you get anxious, you're in a rush or whatever, and you overlook the little detail of, oh, this is a velocity versus time graph and not a position versus time graph. So always important to read them. Okay? All right. From this graph here, the position versus time graph, how can I calculate the velocity?
Y equals mx plus b.
Okay, I can use y equals mx plus b. I don't have the equation on there, but I can figure it out pretty quickly. Okay, here's b, it's 100. Okay, I'll just use this last point here for y because it just happens to be at a grid intersection where I can figure out what y is, and it would be 1400. So I'll have 1400 minus 100, so there's y minus b, okay, divided by x, which is 5 seconds. So 1300 divided by 5 is 260, I think. Okay, and that's going to be in meters per second. Okay, so we just said these two graphs are showing the same thing. Are they showing exactly the same thing? Well, I just figured out that the velocity according to this graph is 260 meters per second. 200, 250, that looks like 260 to me. Okay, these two graphs are of exactly the same thing. Okay? From this graph, the position versus time graph, how can I calculate the total displacement?
V equals V over T.
Nope, we don't want to do.
Rearrange it so then it's D equals V times T.
If I didn't already have this, how would I do it? Because I could do it that way now that I have this, but it's extra steps. What's an even easier way?
Take the y value at the end of the line.
Okay, I could do that as long as b was
Oh, right.
0. How do we calculate displacement?
Well, won't it be 0 since it started at the same point?
But it didn't start at the same point and end at the same point.
Final position minus initial.
Final position minus initial position, right? This is a position versus time graph. In fact, it's what I did right here at the top of the equation, right? I went final position minus initial position, which gets displacement, and divided by time. That's how I got the velocity, okay? So my overall displacement is 1400, the final position, minus 100, the initial position, which is 1300 meters. Okay? Could I get the displacement from this graph? Okay, how?
D equals V.
Right, now I would use V equals d over t. Because what does this graph show me? It shows me velocity, it shows me time, okay? And I can use those two things to get displacement, especially since this object is traveling at a constant v. Okay, I can just use average v, okay? So I can go d equals average velocity times time. Well, that'll be 260, because that's the average, stays at that the whole time, times 5 seconds. Well, right over here, I did that same calculation to get the 260, so 260 times 5, it better still work out to 1300 meters, okay? And it does. Okay, what did I essentially do here? Like, I took 5 seconds and I multiplied it by 260. Yeah, I found the area underneath the line. Okay? That will always get you displacement on a velocity versus time graph. It's not something I want you to memorize, but you probably memorized it in Science 10 anyway. Okay? But I kind of want you to understand why it works. Okay? The reason that going base times height and getting the area gives me displacement is because when I do that, I'm taking time and multiplying by average velocity. I'm doing this calculation. Okay, I'm just using V equals d over t. Now, will that work if actually I won't make it quite that long. Let's just go to, whoops. Could I still do that if my line wasn't horizontal? Here. Yes, I can. I can do it as long as my line is uniform. Okay, now, what is that line showing an object doing? Accelerating, yeah. Okay, increasing its velocity in a positive direction. Okay, it's accelerating. It's showing the velocity is clearly changing here, right? What would that line look like on this graph? Exactly. It would show an object doing this. okay? Changing its velocity. All right. So now I've got this line here, and I still want to do this. I still want to use average velocity times time. Well, since this line is diagonal, it means I'm changing my velocity by the same amount every second. Okay? I'm accelerating uniformly. So my average velocity is going to be halfway between my initial velocity and my final velocity. Would you agree? Okay? Because if I'm doing that, half the time I'll be going faster than that number, and half the time I'll be going slower than that number. So the halfway point would be my average velocity. How do you calculate the area of a triangle? Base times height divided by 2. If I divide the height by 2, is that getting me the average velocity? It is. Okay? Because on the y-axis, my height is velocity. And we just said, if I'm changing it at the constant rate between here and here, halfway up will be my average. Base times height divided by 2. It'll work. Okay? I just want you to understand why that works. Okay? Because I don't want you to get in the habit of memorizing little tricks for each graph. Okay? If we take average velocity and multiply by time from a velocity versus time graph, we can get the displacement. Okay? So for this one here, okay, we would go 400 minus 100, so 300, okay? And then we divide that by 2, so that would be 150, and then we can multiply that by the time, 5. 600 and 750? I think it's 750, yeah. Okay. Okay, so the displacement of that object will be positive 750 meters over that time. Everyone okay with that idea? How that works? Okay. Back in Science 10, you learned, so I'm just going to erase all this stuff here. You learned this formula. You learned that acceleration equals final velocity minus initial velocity divided by time. Okay? That was the only acceleration formula you had. Right? So this object here, the diagonal line, we already said, is accelerating. Could I calculate the acceleration? Yeah. Could I use that formula to do it?
Yep.
Okay, I could. Why?
Because your
Yeah, go ahead.
because your initial velocity is 100 positive 100 meters per second, and your final velocity is positive 400 meters per second, and then you have your time, which is constant.
Right, so I've got all the pieces to the formula, right? Is there an equivalent formula that has the same form but different letters in it?
Velocity. Because velocity is final displacement is subtract initial
This one?
position, I guess.
Yeah, okay. Yeah, so that would be how I would get something about this line. I was actually thinking of something else. You're totally right. You saw right through my question.
N equals y minus b over x.
Both of those formulas are derived from the slope of their graph. Okay? Acceleration is the rate of change of velocity. And so when I go VF minus VI divided by time, I'm really calculating the slope of that line. Okay? On a position versus time graph, when I calculate the slope of the line, it gives me velocity, the rate at which I change my position. So anytime you have a graph and you're wondering what the slope is, okay, you can just look at what's on each axis, okay, and figure it out. It'll be the rate of change of y divided by x, okay, or the change in y divided by x. That gives you the rate of change of y. Okay? In this case, it's acceleration. Right? So that's where that formula that you used all through Science 10 physics comes from. Okay? We'll still use it in Physics 20 along with a bunch of other acceleration formulas, about 5 more. Okay? but they all basically come from graphs in some way, shape, or form. Okay. Making sense so far? Now, what if I change this line's position to look like that instead? So now it goes up to 500. Yeah. And starts at 200. Is the acceleration still the same?
Yes.
It is, because the slope is still the same. I didn't change the angle of the line, so the acceleration is the same. Is the displacement the same?
Yes. Well, no, because you're going fast.
Right, I'm going faster initially now, okay? So my displacement will be different, okay? So before, we just did average velocity times time, and that worked, provided we had just the kind of a linear line. But here's the problem now. Now, I have to account for the fact that when this started, I was already moving at 200 meters per second. Okay, so now that whole area under the line thing, okay, has to account for not only how far I go while I'm accelerating, but how far I would have gone if I just kept traveling at my initial velocity. Okay, so that's going to be one of the new formulas that we're going to use, okay, or going to learn, and that is this: that displacement equals initial velocity times time plus 1/2 AT squared. Okay, so we just said if you calculate the area under the line, you get the displacement. Okay, is this a rectangle? How do I calculate the area of a rectangle? Length times width, or base times height. Is this the height of my little rectangle? It is, right? This is VI times time. Is that the base of my triangle? Okay, so that's VI times T. This here is 1/2 AT squared. Okay, takes into account that it's accelerating, okay, and uses the average of that along with time to get you the displacement. Okay, you add those two things together, and you get the total displacement. It's still the area underneath the line. Saves you having to do a lot of like measuring and reading on the graph. Okay, if you can just get a couple of points. Okay, whatever with that so far. All right, what's happening in this graph?
He accelerates the runner accelerates in a positive direction, and then he runs at a constant speed, and then decelerates in a
Okay.
negative.
Or accelerates in a negative direction, yeah. Does he actually come to a stop? Looks to me like he does. Right? This is a velocity here of 0, right? The line comes down here and there's nothing after that, so according to the graph, he does stop. Okay, his final velocity is 0. Right? Yes, that's exactly what's going on in the graph. He accelerates, then runs at a constant velocity, and then comes to a stop. Okay, so accelerates negatively until he's stopped. Right? This is what any sprinting race graph would look like. Right? All that changes is how fast can you run. Okay? It changes the position and possibly the angle of the two accelerated parts. Okay? This person is not very fast. Okay? I know 8 meters per second sounds like that's pretty fast, but in terms of like sprinting speed, that's not very fast. Okay? Usain Bolt, 17 meters per second at top speed. Okay? Now, probably some of you are doing the math in your head going, then how come he can only run the 109.3? He has to accelerate. And Usain Bolt is one of the worst accelerators there is. The guy's a freak athlete, make no mistake, but his acceleration and his start, terrible. And they always have been. If you watch him like race throughout his career when he was just a young man, he was never good out of the blocks. He might as well have just stood there without starting blocks and started running when they shot the gun. Okay, for all the good the blocks ever did him. He's always the last guy out of the blocks. But if you ever get a chance, watch one of his races and watch the other people in the race. Because they all have a head start because he's such a terrible starter, but you can all see them doing this about 70 meters in. Okay, because they can hear him coming. They don't get a lot of chance to hear him coming because he runs the 100 in 30 steps. Okay? I mean, think about it. When you're running at 17 meters per second, think how much distance you cover in one stride. Okay? Yes, at first he's got the choppy little steps that all sprinters have at the beginning, but once he's at top speed, it's like he's flying. Okay? His feet hardly ever touch the ground. Okay? It's kind of freakish to watch. So his graph would be more like this. Okay? But his top part here is actually fairly short. Okay? The rest of the sprinters in the race look like this. Okay? They reach their top speed quickly and maintain it for a lot of seconds. Usain Bolt accelerates slowly to a freakish speed, okay, that he can only maintain for about the last 30 meters. Okay? It takes him 60 meters to accelerate. Okay? Really good sprinters can accelerate in 35 to 40. That's why the test of your sprinting ability is the 40. Okay? 40-yard dash. Okay? That's how quickly you should be able to reach your top speed. That sort of makes sense? Okay? This is why Usain Bolt is actually a better 200-meter runner. Okay? He doesn't get any glory for the 200, but he also holds a record in it. Okay? Because he gets to that speed. Imagine he gets to run at that speed now instead of for 40 meters, but for 140 meters. Okay? Everybody else just falls away, because they have no hope of keeping up with that. Okay? Andre DeGrasse, he's more like this. Okay? So he's our Canadian sprinter. Right? He's also very atypical for a sprinter. You ever notice he's like the shortest, skinniest guy in the race every single time. Okay. Everyone all right with being able to interpret a graph? Because I might ask you to do that, right? Interpret a velocity versus time graph. All right, so when we're reading a velocity versus time graph, the things we can read directly off the graph: velocity, time. Okay? We can infer the direction of motion. We can infer the type of movement. That would be positive acceleration, negative acceleration, or constant velocity forward or backward. Okay? Those are the things we can determine from a velocity versus time graph. Okay? Or that we can infer. To calculate, we can calculate acceleration from the slope, okay, or just final velocity minus initial velocity over time if it's irregular, okay, and we can calculate the total displacement by using average velocity times time and finding the area under the line, okay, on the graph. All right, so those are the things we can calculate and that you'll be expected to calculate from a velocity versus time graph. Now, something to keep in mind here, because I see it sometimes on a velocity time graph. Okay, so let's say I tell you that a person is walking north, right? So I'm going to say that this is north, okay? So this is velocity in meters per second, north, okay? So they're walking north at 4 meters per second. And they do that for, I don't know, 10 minutes. Okay, so to there. Then they turn around and walk south at 3 meters per second for 10 minutes. Okay, how do I draw the rest of this graph? So, like, I just do this.
You can't go back in time.
Can't go back in time. See, that's why I asked that question, is because oftentimes people will tell me that. Oh, well, you just do this. Well, then I'm going back in time. Okay, I'm going back to time 0. I can't go back to time 0. Okay, what I can do is continue forward in time at -3 meters per second, or 3 meters per second south. Okay, so people get confused on this because that looks like they're still going the same way. They are. They're still going forward in time. That is true. They are still going the same way according to the x-axis, which they can do nothing about. But according to the y-axis, they are now going the other way. Okay, they are moving south now, even though time is still passing. Okay, just one of those things to watch for, because I once had that as a multiple choice question, and it got so many people, okay, because I drew it back. And they're like, yeah, back, that's right, okay, undo everything. No, no, okay, you can't do that. All right. All right. Which one of these lines on this graph is showing me the slowest accelerator? Yeah, because it has the right, it has the smallest slope or the least steep line. Okay? What is the blue line's acceleration? 1.28 meters per second squared. All right, now, just in case you forgot from Science 10, okay, when we use the formula, or any formula that calculates acceleration, but this one in particular, okay, what we're doing is dividing meters per second by seconds. The seconds don't cancel here, okay, because in meters per second, the seconds are on the bottom. So it's like doing this. It's like dividing fractions. Okay? If I want to divide fractions, what do I have to do? Multiply by the reciprocal. Okay, so I take the reciprocal, which is 1 over seconds. Meters times 1 is meters. Seconds times seconds is seconds squared. Now, that doesn't mean you need to square the number. The number's not squared. It's the units. Meters per second per second. Okay? The rate at which we change our velocity is often just quoted as meters per second squared because mathematically it's easier in meter to write than meters per second. Okay? All right, everybody okay with that idea? All right. I would like you right now to calculate the displacement of the orange line. So, typically if we want to find the displacement, we find the area under the line, yes? How accurate is the scale on this graph?
Pretty accurate.
Well, it's pretty accurate, but it's pretty hard to read, right? Like I'm looking at here what B would be, right? Like, I mean, I can get it from the equation, which is what I want to do, okay? But if I'm trying to figure out, you know, like how far it's, or, you know, even read any of these numbers, I really can't because the scale's not very good, okay? So let's say, so this thing is going to take 0.3 seconds, okay? We'll just say that we know that. 0.3 seconds to finish, okay, to get to this position here, or to this velocity here. So I'm going to use this formula that we talked about a minute ago. VI times t, I know the experiment only took 3 seconds, okay, plus 1/2 AT squared. Okay, so I know t. T is 3 seconds. What's VI?
Initial velocity.
What number?
Oh, 7.65.
0.285. Okay, remember, that's B, right? My initial velocity is how fast was I going at time 0. So my initial velocity is the y-intercept. Okay, so it's B. So I would go 0.285 times 3 seconds. That's calculating. Okay, remember we've got these two shapes here that we're essentially calculating, right? This is VI times t. This is 1/2 AT squared. Okay?
It's 0.3 seconds.
0.3 seconds, you're right, 0.3 seconds. Okay, and then I would add to that 1/2, where do we get the acceleration from? The slope, yeah, 7.61 times 0.3 squared, right? That'll tell me the displacement of that object. Eventually. All right, so that thing is going to travel 0.43 meters, 43 centimeters. Forward. Okay? Spoiler alert. that graph is actually from the lab that we're gonna do later. Okay, when we do our accelerated motion lab, we're gonna get data that looks just like this. Because we're gonna run 4 trials with those same carts we had. We're just gonna have ramps. Okay, we're gonna start with a ramp that's not very steep, move up, move up, move up, get 4 trials, okay, and do some analysis of it, of the velocity versus time graphs. Okay, and we'll get something like this. This would be our first trial, second trial, third trial, fourth trial, fifth trial. Okay, as we got steeper and steeper and steeper, the acceleration would increase. Okay, I would like you guys to try number 6. It has to do with that graph there. Okay, I think you guys can read all the numbers you need off of that. Okay, this one will not use the d equals 1 bit plus 1/2. Okay, this one will be more about shapes. Okay, but I'll give you guys a little bit of time to try that one. Okay, let's just look at the first 3 for right now, because they don't involve you having to really do any math. Okay, so average velocity during segment A. All right, what's going on in segment A? It's accelerating, and it's accelerating from 0 to 40 uniformly. That means the average velocity is where? In the middle, halfway. Okay, half the trip it's going faster than 20, half the trip it's going slower than 20. Average velocity is 20, okay, for the first part, because it's accelerating uniformly from 0 to 40. Okay, now the second part's easier, because for the entire part, it travels at 40 kilometers per hour. So that part's easier. Or meters per second, sorry. Okay, and then here, okay, in this last part, we accelerate uniformly from 40 to 80. So the average would be 60, halfway in between. Okay, so that part there, that's why that whole thing with the, the half, okay, works when we're doing the base times height stuff. Okay, all right, if I want to get the average velocity, what 2 things do I need?
Total time
And total displacement. Okay, can we get total displacement from this graph? Okay, and we can read total time right off the graph. Okay, I'll give you a few minutes to see if you can get the rest of it. So in the first part of this graph, the object is accelerating, okay? And it's accelerating uniformly, so we could calculate its displacement simply by using average velocity times time, which would be the area of that little triangle. Okay, so the height of that triangle is 40, okay? The base of that triangle is 20, okay? And we would have to divide by 2, so 20 times 40 is 800. Yeah, divided by 2 is 400. Okay, then the object travels at 40 meters per second for the next 30 seconds, right? That means all the way along here. But what do I have to take into account for the last part? Yeah. Okay, I still need this box here as well. Okay, that's where that formula D equals VI times T plus 1/2 AT squared comes from, right? This would be the VIT part of that. This would be the 1/2 AT squared. But I just said you didn't need to use that formula. You don't, but you do need to take into account that bottom box, because if the object didn't accelerate, it would have kept doing this, and that would be part of our area. When it accelerates, we still have to take that area into account, because it would still be doing that plus the additional distance it covers while accelerating. Okay, so this part here is actually one really, really big rectangle with a small triangle on top of it. Okay, so this would be 40 times 40, right? So 1600. Is that right? Okay, and then this little box here has a height of 40, okay, and a base of 10, right? So 40 times 10 is 400, divided by 2 is 200, okay? And so that's going to mean 1,800, 2,200 meters, okay, is my total displacement, okay? And my total time is 60 seconds, okay? I don't know why I have kilometers per hour on there. That's weird. Okay.
Yeah, because it actually be like 2 kilometers an hour for the day.
Yeah, so I must have put the wrong graph up here. Weird that the numbers were right, but the units were wrong. Okay, so 2,200, okay, divided by 60 seconds. Okay, gives us 36.7, actually we only have 2 sig digs here, so we would say 37, that should be meters per second. On there. All right. Everybody all right with that one? So that's a pretty typical one, like you could get on a quiz, okay, or even on a unit exam. I probably wouldn't have one that would have 3, probably just 2, but okay, something like that. Okay, so at the end of a school day, student A and student B say goodbye and head in opposite directions, walking at constant rates. Student B heads west to the bus stop while student A walks east to her house. After 3 minutes, student A is 300 meters east and student B is 450 meters west. All right, so graph the position of each student in one graph, right? Well, that would look something like this, okay? One of the students is moving east and one of the students is moving west, okay? And do we notice a difference in slopes there?
No.
Yes.
Yeah, the student moving west or into the negatives goes further in the same amount of time. So that bottom line is a little steeper than the top line, okay? Because it says here, the person who's walking east only goes 300 meters. The person who's walking west goes 450 meters. Okay, so you can see this line here, the distance here is greater than the distance there, right? So all that graph is meant to show is the importance of having a positive and negative part to your y-axis when required. Okay. Okay, so if we have a wildlife biologist who's measuring the time it takes to reach a certain displacement, that would be a position versus time situation. Okay, so the elk takes 10 seconds to go 200 meters. Is that pretty fast? They'd run Usain Bolt into the ground. Okay, it takes Usain Bolt like 18 or 17 seconds to do the same thing. Okay, it only took the elk 10 seconds to do that. Okay, a coyote, 10.4 seconds, also pretty fast. Okay, a grizzly bear, 18 seconds. Should you try to outrun a grizzly bear?
No.
If you're Usain Bolt and there's no obstacles, yes, you have a chance. Okay, if he can run, yeah, but he might have better endurance than you. The problem is that you never encounter a bear in a place where there are no obstacles. And if you've ever seen a bear run through the trees, that's what they do. They literally run through trees, like small ones. They just break them right off like they're not there. Okay, and that can be trees that are that big around, even that big around. Okay, they got those broad shoulders. Okay, they hit those things, and they just break right off. You or I hit one of those, and we bounce off of it. Okay, so yeah, you got no hope. Okay, on outrunning a grizzly bear. Your only hope is to hike with a partner who's slower than you. That's what I always did. Okay, I always made sure whoever I was backpacking with was slower than me. Okay. One of my backpacking partners, he was my best man at my wedding. He's 5'4", okay, about 200 pounds, because he used to be a wrestler. And I was like, yeah, I always go hiking with you, man. You're a great hiking partner. Why? Because you're slower than me. He goes, yeah, but I'm closer to your knees than you are. I'm like, huh? I'm taking that. Okay. All right, so just be aware, yeah, you got these different speeds, that they could run at, and obviously that means they're going to have different slopes because your slope equates to your speed. Okay, what's this object doing? It's what? Being what? Nope, not being thrown.
Slowing down.
It's slowing down. Okay, this is a position versus time graph, right? And the amount of distance covered every second is getting smaller until it's basically nothing at all. Okay, the line's getting flatter. That means the slope is getting lower and lower. And on a position time graph, the slope equates to the velocity. So this object is slowing down and coming to a stop. What would this look like on a velocity versus time graph?
Would it like be angling down a little bit? meters in the
It absolutely would. It would look like that. That's an object whose velocity is decreasing or is accelerating negatively and coming to a stop because the line stops at 0 at the x-axis. Okay, so it would look like that. Sometimes you get a question like that. Here's a position time graph, draw the velocity time graph, or vice versa. Okay, and so we got to be able to kind of analyze, oh, right, okay, on this graph, this is what's going on. That's what we did. We went, okay, it's a curve, so its distance is decreasing. That means it's slowing down. That's what's slowing down on the velocity time graph is. Okay. This is a velocity versus time graph. I would like you to calculate those two things, the total displacement and the average acceleration over the whole trip. Okay, so not slope in this case because it's not a single line. Okay, but you can still calculate the acceleration over the whole trip and the displacement over the whole trip. Right? I'll give you a few minutes to try that. So to get our displacement then, okay, we would have to identify our shapes. I would say it's those three shapes. Okay, we have a rectangle that has a base of 4 and a height of 3. Okay, and we're just going to pretend that that's in seconds, like you probably all did. Okay, and then this here is the triangle is going to have a height of 2 and a base of 1. So 2 times 1 is 2, divided by 2 is 1. And then we've got the rectangle, it's got a height of 1 and a base of 6. Okay, so we'd be looking at 19 meters. Actually, not positive, east. How did I know it was east? It tells me on the y-axis. Always look, okay? Sometimes they put positive and negative, but they actually write after the label which direction is positive, okay? Just so that you know. All right, to get the acceleration, I use my science 10 formula. Acceleration equals final velocity minus initial velocity divided by time. Okay, my final velocity is 1. My initial velocity is 3, and that takes 10 seconds. So, negative 0.2 meters per second, okay? Or actually, 0.2 meters per second squared west.
Still going so much east.
Oh,
Because
it is, but it's accelerating west. I don't disagree with you. You're absolutely right. It is still going east, but because it's going slower at the end, its acceleration is west, right? Because it's
Really-
slowing down east.
That's really confusing because you're still on the positive.
Yet you're still in the positive. Remember, this graph is showing me my velocity, and my velocity is still east. And it's possible for me to move east while accelerating west, in the same way that it's possible for me to move up while accelerating down, like this marker right now. Right? As soon as it leaves my hand, it's accelerating down, but moving up. Possible for that to happen, right? It's just slowing down, which is what this object is doing in general over the course of the entire operation, right? Still moving east, but doing so slower than it was at the beginning. Okay. This is the one I always put one like this on the test. Always. So bird starts flying south. Okay, so the negative part of this graph is south, and it's a velocity versus time graph. Okay? I would like you guys to do those three things. Okay, so for part A, you're just indicating whether the acceleration is positive, negative, or 0. The value of the acceleration whenever it's not 0. And at what time does the bird change direction? Okay, I'll give you a couple minutes on that. Okay, yeah, so we got the -2 over 1, so our acceleration is -2 meters per second squared, which it would also be here because it's exactly the same thing in part C. Okay? And then in part B, obviously 0, part D is 0, okay? Part E, we go from -6 to +6, which is a change of 12. Do that over 3 seconds, okay? +12 divided by 3 is +4. Positive is north, 4 meters per second squared north, and then F is 0. Here's the most important part of this question. It's what I've always put on your unit exam. At what time does the bird actually change direction?
8.5 seconds.
8.5 seconds.
Why?
Okay, how many people wanted to say 7 seconds? Okay, at time 7 seconds, the bird starts to accelerate in a forward direction. But at time 7 seconds, its velocity is still negative. Okay, its velocity becomes positive here at 8.5 seconds. Okay, all along this line, it's accelerating north, but it doesn't start moving north until it comes to a stop somehow in the air without falling. Okay, and then starts going actually north. So accelerating north all along this line. But it only starts to move north when the velocity actually becomes north.
So that's when it like turns, that would be the point where it turns around, but it's already been accelerating to the turnaround.
Yeah. So it's hard to imagine that with a bird because
Yeah.
it would be going around a curve, right,
That's a
in
bad
order to
analogy.
turn. A better analogy would be the one I used the other day where I run into a bungee cord. Okay? So if there's a bungee cord strung across the front of the classroom, okay, I hit the bungee cord, I'm already accelerating to the other side of the room, but I'm still moving this way. Okay? My velocity doesn't become positive until I stop and actually start moving towards the other side of the room. Okay? The entire time, the bungee cord is pushing me that way, and I'm accelerating that way. But I don't actually start moving that way until halfway through. Okay, does everyone follow the difference there? You can. Okay, so that's an important one. I almost always ask that just because that's one of those higher level graphical analysis type of questions. It doesn't require you to do any calculating. It just requires you to interpret and analyze the graph skillfully. Okay. No. No. All right, I would like you guys to try 7 and 8, please. Okay, so we're looking for the displacement here in this first graph. Okay, we have two different sections. What's going on in the first part? Traveling at a constant velocity of 5 meters per second east. Okay, like if I was asking that on a test, that's what I'd be looking for a full mark answer. Okay, I can get all that from the graph, so it's all important information. Okay, I know the velocity is constant. I know that it's east because the graph tells me so. Okay, all right. So if I'm doing this graph, the areas I would have to calculate in order to get my total displacement would look like that. One large, long rectangle and one triangle. Okay, so I would have 5 times 10, so that would be 50, and then my triangle goes from 5 to 15, so 10 times 5 is 50, divided by 2, this is 25, so we should have a total displacement of 75 meters east. If you didn't write east, did you get it right?
No.
All right. How many people have done the second one? Okay, so look at the second one too. Okay, so calculate the displacement from the velocity versus time graph below. All right, so I would have probably those 3 sections to be looking at for my total displacement. Now, what about this graph is physically impossible?
Instantly accelerating or decelerating?
Yeah, it instantly changes velocity from one velocity to another. Nothing can do that, okay? It violates the laws of physics. You must actually have some period of acceleration to change your velocity. Nothing can instantaneously change its velocity from one thing to another.
Could you just get the volume of the whole thing and just minus the little cutout?
Yep, same thing, mathematically it's the same thing. Okay, so we would have 5 times 4, so that would be 20 meters, and then we would have 2 times 2? Yeah. Okay, so that'll be 4, and then this one here is 4 times 3, which is 12. So we got 36 meters up on that. Okay? Is that making sense to everybody? All right. So these are the kinds of things you could run into. So we're not going to spend a whole lot more time on graphs simply because you did all of this in Science 10. This is just to review the graphing stuff. Okay. Intention tomorrow is to move on to acceleration. Okay. Because we have mass tomorrow, and I'm not sure what time we'll get back from that. I feel like it's going to be kind of into period 2. Okay. By the time we get back from the church, there will be no quiz tomorrow. Okay. So no quiz tomorrow, but we will be moving on to acceleration. Okay. Reminder that your lab that you did yesterday is due on September 26th. Okay. If you want some feedback on your lab report, come in and see me at nighttime or at lunch. Okay. Or at after school or before school. Okay. Pop in and I can go over that with you. That I'll only do in person though. Don't email me at 11 o'clock when you do it and give me some feedback because I won't even answer you. Okay. But come in and see me in person. No problem. No, there just won't be a quiz till today.